smallest particles of matter, until the discovery of the electron, then the proton, and finally the neutron. We continue to believe that protons, electrons, and neutrons were the smallest particles of matter. In 1964, the quark model was introduced, once again proving us wrong. Quarks make up protons and neutrons and are the base of all matter. Protons and neutrons together are called nucleons.
Quarks are elementary particles, that is, particles that cannot be further split. There are 6 types of quarks, also called flavors: up, down, charm, strange, top, and bottom. For each of these quarks, there is an antiquark, which adds 6 more quarks: anti-up, anti-down, anti-charm, and so on. Basically, anti just means that both the particles have the same mass, but opposite electric charges. Up, charm, and top quarks have a charge of 2/3, and down, strange, and bottom quarks have a charge of negative 1/3. All quarks have the same spin of 1/2, but they all have a unique mass. The up and down quarks are the most stable and most common, and because of which, yep, you guessed it right, most stuff is made out of them.
We know that there are 3 quarks called valence quarks that determine key properties of nucleons like spin, mass, and electric charge. But there is a sea of other quarks and antiquarks in a nucleon.
A proton is made up of 2 up quarks, each with a charge of positive 2/3, and 1 down quark with a charge of negative 1/3. This adds up to positive 1, the charge of a proton. Likewise, a neutron is made up of 2 down quarks and 1 up quark, canceling out to 0, the charge of a neutron.
So what about that sea of quarks and antiquarks in nucleons? And how come there are 3 valence quarks?
The 3 valence quarks are a result of subtracting the total number of quarks from the total number of antiquarks. As long as there are 2 more up quarks than anti-up quarks, and 1 more down quark than anti-down quarks, and the quark-antiquark pairs cancel each other out, the frenzy of quarks and antiquarks can continue whizzing around, popping in and out of a nucleon.
But what is holding these hyper little things from flying all over the place? The answer is the strong force. It is one of the 4 fundamental forces, and as the name indicates, it's pretty strong, the strongest in the world.
Gluons are particles which bind quarks together. They are the force carriers of the strong nuclear force. The closer quarks are to each other, the weaker the binding force is. The farther quarks are from each other, the stronger the binding force is.
Quarks have cleared up many mysteries, like why in some instances neutrons act as if they have electric charges, and why electrons bounce off of protons in ways that would only make sense if a proton was made of smaller pieces rather than a whole ball of positive charge. Deepening our understanding of quarks and how they interact is key to truly understanding our universe.